Hey everybody, that's a baby cucumber. Be quiet, because it's sleeping. Anyhow, the thing about this baby cucumber is it'll grow up nice and strong if this part of it, right there, has collided with bee's fanny. I think that's what they call it in biology. And so sometimes processes need to have a collision, and that's what second order reactions are. But today we're going to basically calculate some things with the second order reaction equation, and so it's not as relatable as first order, but neither is trying to equate a cucumber to second order. So let's just go and talk about second order reactions right now. Hola everybody, hola, ¿qué tal? Miguel here, and today we're going to talk about second order equations or reactions. And so I've got some good news and some bad news with regard to the second order reaction equation. First of all, if you go and take a bunch of math that does not fall under the scope of this course, if you take rate equals K times A, which is the reactant to the square, and you integrate that so you get a function of concentration versus time, you get this equation, which does not have any logarithms in it. It's a different kind of curve. It's an inverse function, where this would be 1 over x versus y, that sort of thing. It's still a curve, so anywhere on this curve you would have the concentration of A at any particular time. And so if you wanted to go and calculate a time or a concentration, it would come out of this equation. There's concentration, there's time, and looky there, you got rate constant K. So what we're going to do now is solve some problems. And the good news about there not being any logarithm in it is accompanied by the fact that you don't really have a very good landmark like half-life with first order. So let's try an example problem right now. All right, we're gonna launch into some skill building. So first of all, your first skill is to ignore anything that seems like trivia. And we're reading through this stuff for just facts. And as much as I'm sympathetic to nitrous acid and yada da, decomposes da 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 da, I see second order reaction. I see that. As soon as I see second order, they gave it to me. They gave it to me like a gift. Now I know the equation to use is 1 over NO2 initial minus 1 over NO2 equals KT. That's not the natural log one. That's for first order. And so what you basically have to do there is realize that that's in your toolbox, and that is what we're going to do first. So now here's the, oh, and look what I did. HNO2, Mike. HNO2. All right, and that's going to be our toolbox, and that is going to be what we will do to solve this. Now, okay, if the initial concentration is 0.156, bang, initial concentration. Concentration of HNO2 initial. So if that's the initial concentration, and at a time of T, 1,000 minutes, the concentration has decreased to 0.1466. This is HNO2, not initial. And so that's that equation. That's, oh my goodness. Mike, what are you doing? Oh, don't look at that. Mike goofed up. He had the initial in that. Okay, so we fixed that. So back to what we're talking about. Here is Boy, we got a lot of stuff. Here's another T. What? So what they're saying, though, if you read this carefully, is that the initial concentration is 0.156. At a time of 1,000, 0.1466. What would the concentration be at a time of 3,000? So if I go ahead and write out the equation correctly, then take inventory of what you got and what we were given. They gave us a lot. It almost is too much. And what they did is they gave us, here's 0.1560 is the initial concentration. My bad. See, there's no negative in this equation. That's another nice thing. We don't have any negative in that equation. And that's why you see when I goofed it up before, you would have caught yourself. I would have caught myself, because initial concentration's bigger. 1 over concentration initial is a smaller number. It should be bigger number minus smaller number so that there is no negative. And that's why I noticed that I jacked it up. And that's the way I wrote it earlier, thank goodness. I was just daydreaming while I was talking here, thinking about the next thing to say. So if you see that I have that variable there, I have that variable there, that variable there, that variable there, I have a t, then I can solve for k, but remember this t of 1,000 is under these conditions, and the other t is at some other conditions where I got to solve for concentration. So I'm going to plug in these three numbers, and then we're going to go ahead and solve for k. And so this was a fancy way of them disguising that we need to solve for k. Just like last time, we need to be given a k, you need to find out a k, or you need to calculate it. So they didn't tell us that we needed k, but that's the only thing missing. So I'm going to go ahead and plug in, and watch out if you get it backwards. To be honest with you, if you get it backwards where you got smaller number minus bigger number, just take the same value, but then it's got to be positive. So just make sure that that's positive on each side. So let's go ahead and plug all that stuff all up in there. So this would be 1 divided by 0.1466 moles per liter minus 1 over 0.1560 moles per liter. And that would be equal to K, which I don't know yet, times 1,000 minutes. So let's do some quick and fancy math here. Now, no logarithm button. That's kind of nice, but that's about where the niceness ends. I'm going to go ahead and do that. This is 6.82 liters per mole, because I took 1 over concentration. So it's liters per mole. That might be a little weird, but that's what it is. And then minus, if you have an inverse button, you can use that too. 0.1560, 6.41 liters per mole equals K times 1,000. Solve for K. K is going to be, if I do that subtraction, well, geez, Mike, that's just 0.41 liters per mole divided by 1,000 minutes, and that's going to be our K. So I don't know why I have to do it on a calculator, because I'm scared that I'm going to goof up by not including a 0 like I've done before. So this would be 4.1 times 10 to the minus 4. That's K. By the way, units, liters per mole per minute. If they give you the constants units, that tells you something. And by the way, that jives with the equation, because both sides of the equation have to have units of liters per mole, because that's 1 over molarity, and then this has to have units of time. So K for second order will always have units of liters per per mole per time. Whatever the units of time are is whatever's convenient. So now what we're going to do is we're going to go ahead and answer the question by plugging back in K to solve. So now it's going to be find concentration of HNO2 at that time. So what do you want to call it? I want to call it X. 1 over X minus 1 over HNO2 initial. Now look, I did all the work of finding 1 over concentration initial. I'm not going to do it all over again. 6.41 liters per mole. And that would be equal to K, 4.1 times 10 to the minus 4 liters per mole per minute, times 3,000 minutes. So why don't we do order of operations on the right side, and we will go ahead and find out what the heck 4.1 times 10 to the minus 4 is times 3,000. That'll be 1.23. Okay, now this is where things get kind of tricky here. You make sure you keep track of your units. The minutes in the denominator cancel the minutes in the numerator, so this is liters per mole. Over on the right, this left, this is still minus 6.41 liters per mole. So what I'm going to do is I'm going to find the 1 over X, so plus both sides. I'm going to add 6.41 liters per mole. And I'm out of paper. But guess what? I got more paper. Bang. Okay? And so what we're going to do now, that of course will be 1 over X equals whatever 1.23 plus 6.41 is. I left the 1 out when I started panicking due to my lack of paper. All right. So we'll go ahead and we'll find out 1 over X is whatever 1.23 plus 6.41. 7.64 liters per mole. Okay, now what do we do? That is not the concentration. That is 1 over the concentration. So we'll do a 1 over on each side. So I'll do a 1 over X, an inverse, if you will. If you got an inverse button on your calculator, comes in awful handy right now. And I did an inverse of that side is 0.131. Now, 1 over liters per mole is moles per liter. All right, so does that make sense? It doesn't not make sense, because what happens is, you know that at 1,000 minutes, it was at 0.1466. Now, once in a while, you know what, people will goof up accidentally. Maybe they'll get this part wrong, and instead of inverting it or whatever, they'll get that wrong, and they'll have some number that don't make sense. Now, what would not make sense? Now, I don't have half-life to lean on with second order. I really don't. But what I do have is I could say, well, at least it's lower than the value was at 1,000 minutes. And so, it sort of makes sense to me that 0.131, but you don't have half-life like you do with first order. So that's a little bit of a bummer. Hey, another question. How long would it take for the concentration to diminish to 0.078? So a continuation of this, but what would make it go down to 0.078? And you know why I picked that number when I thought this problem up? That's half. How long does it take for it to go down to half of the initial? So I'll go ahead, and this time I have the same equation. I'll write it with a fatter pen this time. 1 over concentration of HNO2 minus 1 over concentration of HNO3 NO2 initial equals K, which we know, T. So we'll go ahead, and this time we're asking how long is it going to take for this to go to that value. That's the reactant to get to, that's HNO2, not initial, of course. So I'm going to go ahead and plug it all in. 1 divided by 0.078 moles per liter minus, same stuff as before, 6.41 liters per mole per minute equals 4.1 times 10 to the minus 4 liters per mole per minute. And what's missing? How long? T. So you see, you got to really kind of read this and like say, what do you want, problem? Right? What would the concentration be? That's the concentration part of the equation. This time they're saying how long. That's the time part of the equation. And so we're solving for T in this problem, folks. And so that's the whole goal of this. Let's go ahead and do that inverse. So 1 divided by 0.078 is 12.82. 12.82 liters per mole minus 6.41 liters per mole. I goofed up and put minutes in there. And then if I wanted to go and get fancy, that would equal 4.1 times T, 4.1 times 10 to the minus 4. But I'll go ahead and divide that. I don't think I'm going to lose anybody here. Liters per mole per minute. That would be what T is. And I think you'll notice that when we do that subtraction, I'll write it over again. So 12.8, it's 6 point, and it's twice. I chose that number because it's half. So 12.82 minus 6.41 is just 6.41. Then I'm going to talk about that in just a second. 6.41 liters per mole divided by 4.1 times 10 to the minus 4 liters per mole per minute equals T. So 6.41 divided by 4.1 times 10 to the minus 4 is 15,634. What's the units? Liters per mole cancel. And so it's going to be 1 over minutes. Now I'm going to do something here and make a statement. And I alluded to this in the last video, but maybe I didn't quite perfectly. What textbooks will do is they will call this a half-life. And they are correct to call it a half-life. And because that was the time for this to go from 0.1560 to half that. And it's 15,634 minutes. Now we figured out that 3,000 minutes is when it went down to our value that we found of 0.131. And so it's a curve, and so 3,000 minutes is when it went down to 0.131. 0.078 is a lot less than that, and particularly it's half. So what textbooks will do is they'll say that's T1 half. And they're right, but guess what happens if we had to cut it in half again? If you really, really were interested in what we did today, go ahead and find out how long would it take to get to 0.039? Just plug everything in the same. As a matter of fact, let's go do that. So we're going to go ahead and do the same dang thing, except we're going to go plug in 0.039. Now remember this number, because I'm going to make a big old point here and I'm going to get on a soapbox. So we go ahead, we plug in 1 over 0.039 liters per mole. Well, moles per liter in the denominator, and so therefore minus 6.41 liters per mole equals 4.1 times 10 to the minus 4 liters per mole per minute times T. So we're going to find T. 1 over 0.039 is 25.6 liters per mole minus 6.41 liters per mole equals 4.1 times 10 to the minus 4 times T. Okay, hold on. I'm going to make my point in just a second. 6.41. So this is 19.23 liters per mole. Let's divide both sides by 4.1 times 10 to the minus 4 liters per mole per minute. That is T. That would be 46,904 minutes. So how come it ain't double 15,634? It cut itself in half again. That's quarter of the initial concentration. And that's because that ain't how second order works. So great, you know, that's a T. But please, textbooks, and I know textbooks aren't listening because they don't have ears yet, maybe someday. But if you were a textbook and you're listening, quit calling that a half-life, because the whole sort of convenience of knowing what a half-life is that's the interval that it cuts itself in half regularly. That only happens with first order. You go and cut this in half again, it'll be even a longer time out for that to cut itself in half. So the slope of second order is different than first order. It's less steep. And so that's how it works. But you can't say, and it's very distracting to call it a half-life. It's just a time that it cut itself in half is X, and then the time it takes to cut itself in half again is not 2X. And so there you go. And I'm glad you let me talk about this. It's really helped me feel better about myself. And I think I've got a great weight off my chest now that you've let me have my second order half-life rant. So half-life in first order, really valuable. Half-life in second order varies all over the place. So quit calling it something that it ain't. It ain't a constant, textbook. Okay, thank you. I'll catch you guys later when we'll have even more problems, but we'll be able to fix them because we have these two equations at our side at all times. Thanks to the universe. Thank you, universe, and thank you for watching. And hopefully not on double speed, right? Something like this. Okay, see ya.